We are going to start chapter number 4, and chapter number 4 describes the structure and working principles of dielectric slab waveguides. So there are three layers in our dielectric slab waveguide. The refractive index of the central layer is N1, and the central layer is known as film. The refractive index of the top layer is N2, and the refractive index of the bottom layer is N2. So it consists of three layers. The refractive index of the central layer is N1, the refractive index of the bottom layer is N2, and the refractive index of the top layer is N2 as well. So here is the top layer, here is the central layer, and here is the bottom layer of this waveguide. You see, N1 N1 is greater than N2. The refractive index of the central layer of the symmetrical slab waveguide is greater than the refractive index of the top as well as bottom layer. The thickness of the central layer is represented by D. So D represents the thickness of the central layer of this slab waveguide. You see, you guys can consider the rectangular coordinate system. Here is x-axis, here is y-axis, and here is z-axis. So the light ray travels in the central layer of the slab waveguide, and you see, we will consider the interface between the top layer and the central layer, and we will consider the interface between the bottom layer and the central layer. So if you consider the interface between the top layer and the central layer, this y coordinate is normal to this interface. Similarly, the y coordinate is normal to the interface between the central layer and the bottom layer as well. As far as the x coordinate is concerned, x coordinate is tangential to these interfaces. Similarly, z axis is tangential to these interfaces as well. So the dielectric slab waveguide consists of three layers. The central layer is known as film of the slab waveguide. The refractive index of this layer is N1. The refractive index of the top layer is N2, and the refractive index of the bottom layer is N2 as well. So the central ray is known as the film of the slab waveguide, and the light ray travels in the central layer. There are two types of symmetrical. There are two types of dielectric slab waveguides. We have asymmetrical slab waveguide and we have symmetrical slab waveguide. So let us consider the, the structure of the symmetrical slab waveguide and the structure of the asymmetrical slab waveguide. You see, the slab waveguides satisfy the total internal reflection, the total internal reflection or the condition for the total internal reflection. So the total internal reflection will take place, and this total internal reflection will save the light ray in the central ray of the asymmetrical as well as symmetrical slab waveguide. So let us consider the asymmetrical slab waveguide first. So the waveguide will be known as asymmetrical waveguide if the refractive index of the top layer is not equal to the refractive index of the bottom layer. So you see, in this particular case, the refractive index of the bottom layer is N2 and the refractive index of the top layer is N3. So if this is the case, then the waveguide will be known as asymmetrical waveguide. You see, the top layer may be of air, so the refractive index of the air is 1. Anyhow, in this particular case, N1, which is the refractive index of the central layer of the waveguide, is greater than N3, and N1, which is the refractive index of the central layer of this slab waveguide, is greater than N2 as well. So N1 is greater than the refractive index of the top layer of this waveguide and the refractive index of the bottom layer of the slab waveguide. So this type of waveguide is known as asymmetrical slab waveguide. Well, we consider the symmetrical slab waveguide. So you see, in symmetrical slab waveguide, N2 is equal to N3. The refractive index of the top layer will be equal to the refractive index of the bottom layer. So if this is the case, then the waveguide is known as symmetrical waveguide. You see, the light ray travels in the central ray of these waveguides. We don't care whether the waveguide is asymmetrical waveguide or symmetrical waveguide. The ray will travel in the central layer of this waveguide. We know that the thickness of the central layer is represented by small d, and definitely the light ray will travel along z-axis, that is in the central layer of the waveguide. So let us consider asymmetrical slab waveguide. So we consider asymmetrical slab waveguide, and we consider asymmetrical slab waveguide, and we calculate there will be two critical angles. You see, the ray will move towards, let me consider the top layer. Here is the top layer. So we consider the top layer of the waveguide, then we consider the central layer of the waveguide, and then we consider the bottom layer of the waveguide. So here is the central layer. The refractive index of the central layer is n1, the refractive index of the top layer is n3, and the refractive index of the bottom layer is n2. This waveguide is known as asymmetrical waveguide. So you see, we need to satisfy the condition for the total internal reflection. So we consider a ray which travels in this direction. The total internal reflection will take place over here if the angle is greater than the critical angle. So the total internal reflection will take place over here. The total internal reflection will take place over here. The total internal reflection take place over here, and thus the light ray will travel in the film of the waveguide. So we need to satisfy the condition for the condition for the total internal reflection. If we satisfy the condition for the total internal reflection, then the ray will travel in the central layer of the asymmetrical waveguide in the direction of z-axis. So we need to consider this particular angle, which is represented by theta, and similarly we need to consider this particular angle as well, which is represented by theta as well. So let me draw this waveguide once again. So I consider the top layer of the central waveguide. This is the top layer of the central waveguide. This is the top layer of the asymmetrical waveguide, and then we consider the central layer. Here is the central layer, and definitely the ray travels in the central layer, and then we consider the bottom layer of the waveguide. So we consider, you see, this particular angle. If this angle is greater than theta 1 c, then the total internal reflection will take place. So this angle is calculated with the help of this particular equation. Sine theta 1 c is equal to n3 by n1. Similarly, we consider another angle as well. You see, here is the central layer of the asymmetrical slab waveguide. So the ray travels in this direction. If the angle is greater than the critical angle, the total internal reflection will take place. And now we consider this particular angle, which is represented by theta. So this angle should be greater than the critical angle. So we calculate two critical angles in case of asymmetrical slab waveguide. Sine theta 1c will be equal to n3 by n1, and sine of theta 2c will be equal to n2 by n1. So we assume that theta 2c is greater than theta 1c. So the condition for the total internal reflection, we discussed the condition for the total internal reflection. The total internal reflection will take place, and the light ray will travel in the central layer of the asymmetrical slab waveguide. If this angle, you guys can see this angle, which is represented by theta, if this angle is equal to and greater than theta 2c and less than and equal to 90 degree. So we have calculated two critical angles. One critical angle is represented by theta 1c, and the other critical angle is represented by theta 2c. And for the total internal reflection, we need to consider the larger angle. We assume that theta 2c is greater than theta 1c. So if theta is greater than theta 2c and less than 90 degree, then the ray will travel in the central layer of the symmetrical waveguide. So you guys can see that the ray travels in the central layer along, and this ray is traveling along the axis. So in order to save the light ray in the central layer of the slab waveguide, we need to satisfy the condition for the total internal reflection, and here is the condition for the total internal reflection. Now we consider the symmetrical slab waveguide. So this is the symmetrical slab waveguide, and you see the thickness of this central layer is represented by D, and you see the ray travels in the central layer of this symmetrical slab waveguide, and this ray is traveling along z axis. We can calculate the critical angle with the help of this particular equation. The sine of this critical angle will be equal to n2 by n1. So we can calculate the critical angle with the help of this particular equation. So this is the condition for the total internal reflection. If theta is equal to and greater than theta c and less than and equal to 90 degree, so then the light ray will travel in the central layer of this symmetrical slab waveguide, and this light ray travels along z axis. So we can save the light ray in the central layer of the slab waveguide if we satisfy the condition for the total internal reflection, and you guys can see the condition for the total internal reflection in this particular slide. Now we consider the propagation of the light wave in the symmetrical slab waveguide. So we consider the light ray which travels in the central layer of the symmetrical slab waveguide. The propagation constant of the light ray is represented by K1. The light ray is moving towards the top layer. The angle with respect to normal is theta, and the total internal reflection of the light ray takes place over here, and you see this light ray is reflected back to the central layer. So the central layer is known as film of the waveguide. The ray take place in the central layer. So there are two rays. We will consider the ray which is moving in the upward direction, and then we will consider the ray which is moving in the downward direction. Anyhow, we assume that the central layer of this symmetrical slab waveguide is a lossless medium. So we know the equation for the electric field intensity in phasor form in a lossless medium. This is the equation for the electric field intensity in the central layer or in a lossless medium. E is equal to E naught into e raised to power minus j k1 dot r multiplied by ax. Electric field intensity is a vector quantity, and the direction of this vector is given by this unit vector ax. So what we do, we consider the light ray which travels in the upward direction. So let us consider the ray which is traveling in the upward direction. So we consider this ray. You see this ray is moving in the upward direction, and what we do, we resolve K1 into two components. So let us consider the ray which is moving in the upward direction. The propagation constant of this ray is K1, and let us resolve this K1 into two components. So we resolve K1 into two components. One component is along z-axis and the other component is along y-axis. The component which is along z-axis is K1 sine theta az, and the component which is along y-axis, is k1 cos theta ay, and the sum of these two components will give you k1. So k1 will be equal to k1 sine theta az, this is the component which is along z-axis, plus k1 cos theta ay, this is the component which is along y-axis. So the vector sum of these two components gives you k1. Now what we do, we replace k1 sine theta by beta. So we replace k1 sine theta by beta, and we replace k1 cos theta by h. Anyhow, we replace k1 sine theta by beta and k1 cos theta by h, and we consider a three-dimensional vector over here. This three-dimensional vector will have three components. Here is the component along x-axis, here is the component along y-axis, and here is the component along z-axis. And we take the scalar product of these two vectors. You see k1 has a component along y-axis as well as z-axis. So if we calculate the scalar product of these two vector quantities, the scalar product of these two vector quantities results in k1 sine theta into z plus k1 cos theta into y. We replace k1 sine theta by beta and k1 cos theta by y. So k1 dot r, so you see k1, so you see k1 dot r will be equal to beta z plus hy. So we replace we replace k1 sine theta by beta and k1 cos theta by h, and we consider this particular equation. We know that the electric field intensity will be equal to E naught into e raised to power minus j k1 dot r. So this is a vector quantity and this is a vector quantity as well, and this electric field intensity is along x-axis. So we put the value of k1 dot r in this particular equation. So you see this is the electric field intensity of the ray which is moving in the upward direction. So the electric field intensity of the ray which is moving in the upward direction in the central layer of the symmetrical waveguide is equal to E naught into e raised to power minus j hy minus j beta z ax. Now what we do, we consider the ray which is moving in the downward direction. Let us consider the symmetrical slab waveguide, and let us consider the ray which is moving in the downward direction. So we consider this ray is moving in the downward direction. I am talking about this ray which is moving in the downward direction, and we resolve this k1 into two components. You see this k1 will be different than this k1. Why? Because the direction of these two k's are different. They are equal in magnitude but different in directions. So we consider the ray which is moving in the downward direction, and we resolve k1 into two components. So here is the ray which is moving in the downward direction, and what we do, we resolve this k1 into two components. So k1 has a component along z-axis and k1 has a component along negative y-axis. The only difference between these two scenarios, that the y component over here is negative. So we have resolved k1 into two components, k1 sine theta az minus k1 cos theta ay. And then we take the scalar product of these two vectors. R is a three-dimensional distance vector, and R is equal to xax plus yay plus zaz. So we have k1 sine theta z minus k1 cos theta y. We replace k1 sine theta by beta, and we replace k1 cos theta by h. So k1 dot r will be equal to beta z minus hy. So k1 dot r is equal to k1 dot r is equal to beta z minus hy. And we consider the equation for the electric field intensity. We know that the electric field intensity is equal to E naught into e raised to power minus j k1 dot r, and then we have the unit vector ax. So we put the value of the value of k1 dot r in this particular equation. If we put the value of k1 dot r in this particular equation, we get the electric field intensity of the light ray which is moving in the downward direction, and this is equal to E naught into e raised to power jhy minus j beta z plus ax. So there are two rays in the symmetrical slab waveguide. You see, there are two rays in the symmetrical slab waveguides in the central layer of the symmetrical slab waveguides. One ray is moving in the upward direction, the second ray is moving in the downward direction. Definitely these rays will satisfy the total internal reflection. So if we satisfy the condition of the total internal reflection, the ray will travel in the film of the symmetrical slab waveguide. The thickness of the central layer of the slab waveguide is d. So the interference of these two rays the interference of these two rays will take place in the film of the symmetrical slab waveguide, and the total intensity in the central layer of the symmetrical slab waveguide will be equal to the electric field intensity of the ray which is moving in the upward direction, and the electric field intensity of the ray which is moving in the downward direction. So in order to find out the total electric field intensity in the central layer of the symmetrical slab waveguide, we take the phasor sum of the two intensities, the intensity of the light ray which is moving in the upward direction, and the intensity of the light ray which is moving in the downward direction. So we take the phasor sum of the electric field intensity which is moving in the upward direction, and the phasor sum of the light ray which is moving in the downward direction. This will result in the total intensity in the central layer of the symmetrical waveguide. So we take the vector sum or the phasor sum of the two intensities in the central layer of the symmetrical slab waveguide. E1 is equal to E naught into e raised to power minus jhy minus j beta z plus E naught into e raised to power jhy minus j beta z, and we have the unit vector ax. So the first equation can be written as E1 is equal to E naught into e raised to power jhy plus e raised to power minus jhy into e raised to power minus j beta z, and the unit vector ax gives you the direction of the electric field intensity in the central layer of the symmetrical slab waveguide. What we do, we divide and multiply the right hand side of this equation by 2. So E1 will be equal to 2 E naught plus 2 E naught into e raised to power jhy plus e raised to power minus jhy divided by 2 into e raised to power minus j beta z into ax. We know that this quantity this quantity is basically equal to cos hy. So the electric field intensity in the central layer of the symmetrical waveguide. So we know that e raised to power jhy plus e raised to power minus jhy divided by 2 is equal to cos hy, and we replace 2e naught by e1. So you see the electric field intensity of the total electric field intensity of the light ray in the central layer of the symmetrical slab waveguide will be equal to E1 into cos of Hy into e raised to power minus j beta z ax. So this is the phasor value of the electric field intensity of the light ray in the film of the symmetrical slab waveguide. We can write down, you see, the electric field intensity in the instantaneous form. So here is the instantaneous form of the electric field intensity of the light ray in the central layer of the symmetrical slab waveguide. E1 is equal to E1 cos of Hy sine of omega t minus beta z ax. So this is the electric field intensity in the instantaneous form of the light ray which is moving in the central layer of the symmetrical slab waveguide. We are going to find out the velocity or the speed of the light ray in the waveguide. So in order to calculate the electric field intensity of the light ray in the central layer of the symmetrical slab waveguide, we consider the equation for the electric field intensity of the light wave in the central layer of the symmetrical waveguide. E1 is equal to E1 cos Hy sine of omega t minus beta z, and this electric field intensity is in the direction of the unit vector ax. You see, omega t minus beta z is known as the phase of the light wave, and we know that the phase of the light wave is always equal to a constant. So you guys can replace the phase by a constant value. If the phase is a constant value, then we differentiate both sides of this equation with respect to time. So if we differentiate both sides of this equation with respect to time, we get omega dt by dt minus beta dz by dt, which is equal to 0. So we differentiate both sides of this equation with respect to time, and we get this particular equation. Let us simplify this equation now. So we get omega by beta. So dz by dt will be equal to omega by beta. So omega by beta is equal to dz by dt. And what is dz by dt? Dz by dt represents the distance traveled by the light ray per unit time, and the distance traveled by the light ray per unit time is known as the speed of the light ray. We can calculate the speed of the light ray with the help of omega by beta. So this equation is used to find out the velocity of the light ray in the waveguide. That's why this velocity or this speed is represented by Vg. G stands for the waveguide. So this is how we calculate the velocity of the light ray in the central layer of the waveguide. We know that we know that V is equal to C by N. We know this particular relationship, and we know that K1 is equal to K0 into N1. So we know this mathematical relationship and this mathematical relationship as well. So you see, what we do, we utilize this particular equation. We utilize this particular equation where it is. Here it is. So we utilize this particular equation. We know that Vg will be equal to C by N effective. So uh, we consider this particular equation, and we put the value of Vg on the right hand side, and you see the value of Vg is omega by beta. So omega by beta will be equal to C by N effective. So we consider this particular equation. We consider this particular equation. How do we get to see this particular equation? You see, we have Vg. Let me write down the equation over here. Basically, we have Vg, which is equal to C by N effective. And we know that this Vg is basically equal to omega by beta. Okay, so if I put the value of Vg in this particular equation, which is omega by beta, so omega by beta will be equal to C by N effective. And we know that beta is basically equal to K1 sine theta. So beta is equal to K1 sine theta. What I do, I put the value of beta in this particular equation. If I put the value of beta in this particular equation, I get C by N effective, which is equal to omega by K1 sine theta. So we get this particular equation, C by N effective is equal to omega by K1 sine theta. So we go to next slide. Well, C by N effective will be equal to omega by K naught N1 sine theta, right? And we rearrange the first equation. If we rearrange it, K naught into N1 sine theta divided by N effective will be equal to omega by C. And we know that omega by C is basically equal to K naught. We know that omega by C is equal to K naught. So we can simplify the last equation as omega by C is equal to K naught. So K naught N1 sine theta divided by N effective will be equal to K naught, and the effective refractive index of the central layer of the symmetrical slab waveguide will be equal to N1 sine theta. So we can calculate the effective refractive index of the central layer of the symmetrical slab waveguide with the help of this particular equation. So if theta is equal to theta c, then N effective will be equal to N1 sine of theta c, and sine of theta c is equal to N2 by N1. So if we simplify this equation, the effective value of the refractive index will be equal to n2 if theta is equal to theta c. So if theta is equal to theta c, then the effective refractive index will be equal to n2. And if theta is 90 degree, you see, if theta is 90 degree, then the effective value of the refractive index of the central layer will be equal to n1 sine of 90. S sine of 90 is 1, so n effective will be equal to n1, n effective will be equal to n1. So when theta is equal to 90 degree, then n effective is equal to n1. So we know that for the total internal reflection, theta varies from theta c to 90 degree. So definitely the effective refractive index will vary from n2 to n1. This is the condition for the total internal reflection as well. So these are the limits of the effective refractive index of the central layer of symmetrical slab waveguide. Thank you so much. We shall talk about the evanescent wave in the upcoming class. Thank you.